So in this last section of the discussion on musical instruments and sound in general, we are going to take a moment to look at a different type of musical instrument, which we'll use here as the organ pipe. One can think of, for example, the organ pipes that play in a church, which produce very, very loud music, as we know. And wind instruments in general will have this same sort of analysis, but it's easier to understand, I think, with the organ pipe than it is with other wind instruments. So basically the idea of an organ pipe is that air is forced into the pipe in this diagram on the left side, and the air exits on the right. And as air is forced into there, which is usually done by other instruments than the mouth to produce a large volume of air that produces our loud sound of an organ pipe. The observation is that we get the maximum displacement of air molecules that occur at the point where the air is being blown in, which seems quite reasonable. That's where we're getting the forced air coming in to make the sound. And there is the maximum displacement of the air molecules at this end of the pipe, and the air molecules exit the pipe over here, so there's also a maximum displacement of air molecules at the other end of the pipe. What is characteristic of any given wind instrument is the length of the tube between the opening, where we have air being forced in, and the opening where we have air that's allowed to leave the instrument. If we take partially on faith that the largest displacement of the air molecules occurs at the entrance and in the exit of the pipe, then one can show that if they're given that there is a sinusoidal variation not only in air pressure but in the displacement, this particular scenario with A stands for an antinode, whereas node means zero displacement, A means the opposite of that, which is maximum displacement, or A for antinode, then we get one complete cycle of maximum displacement, zero displacement, back to maximum displacement. This then defines the wavelength of the sound that is produced. And because the sound that is produced travels through air at the speed, where in this case it's given by u, which is 330 meters per second, then the frequency of the sound that is produced is going to be the speed of sound divided by this wavelength. Well, in this case right here, the wavelength is 2 times the length of the tube. As I say, it makes one complete excursion from antinode back down to antinode, which is only half of a wavelength. This structure forms 1/2 wavelength, which means that the actual wavelength is twice that. The fundamental frequency will be given by this quantity F1. For example, if we said, for example, that, as we've often said, that the speed of sound is 330 meters per second, and if I had a pipe length which was, for example, 1/2 meter, which would be like roughly 1.5 feet, then we would get a frequency that would be equal to u divided by 2 times 1/2, which is equal to u, which is 330. So the fundamental frequency would be 330 hertz, which would be heard from the sound or the vibrations on the walls of the pipe. So you recall that the violin or the guitar has this wood structure around it, and the wood structure amplifies those vibrations. Well, in this case, the walls of the pipe begin to vibrate at the frequencies produced by the displacement of air inside the tube, and so they will oscillate as well, and they will generate these frequencies with F1, F2, and F3, which are defined by the higher harmonics. So in this case, as in the case, like for example, the rope, the next frequency higher, or the next wavelength smaller than 2L that satisfies the antinodes occurring at the ends of the pipe would be one in which the frequency was twice as high, or the wavelength is half of the one that it had before it, and therefore in the example we just gave, that would be like a frequency of 660 hertz. And then the third one would be 3 times F1, so it would be 990 hertz. These would all be present simultaneously within the same pipe, but with different loudness contributing from each one of these. And that unique combination of loudness at each frequency, when added together, gives us the sensation of tone, or quality that we call it, or timbre. This is the structure that we have, and this is also occurs for other wind instruments besides the organ pipe, but this just gives you one of them to show as an example of using the same concept of fundamental frequency and higher harmonics to generate the sound that comes out as a musical tone. Changing the length of the pipe changes the pitch. If we change L, we change the fundamental. Therefore, we change also the higher harmonics. Two higher harmonics are shown, which are present in the sound. These higher harmonics are F2 and F3. One of them is twice, as we said the last slide, twice the frequency of the fundamental. The other one is 3 times the frequency of the fundamental. And the different intensities of the partial tones when added together give us the unique sound of this instrument. And it will be different whether it's an organ pipe or it's a clarinet or it's any other woodwind or a flute or any other wind instrument. They all have different characteristics, or what we call different timbre, because the contributions of the different higher frequencies is different in every instrument. Now, the walls of the pipe will vibrate at the frequencies of the air in the pipe, which makes the sound quite loud. Again, and I point out, think church organ, and is very familiar with how loud the sound can be from these large organs that exist in that we find in churches. And so, for example, if U was equal to 330 meters, and if L was equal to a half, then I've made a mistake here on my answer, so I'll just make a correction verbally on it. You'll notice that if I take the speed of 330 meters per second and divide by 2L, that would be equal to 1/2 times 2, which is 1, then we get the answers that I talked about before. The fundamental is 330 if the length was equal to ½ meter. But within the church, there you will have pipes of various lengths. So we have a multiple different fundamental pitches that are available by using multiple different pipes that can have forced air blown into them simultaneously. And these will give contributions from different frequencies at the same time. One of the last things we're going to talk about is intensity, and intensity is associated with the perception or the hearing, the quality of loudness that we are more familiar with. Sometimes we call it the volume. Turn down the volume, turn up the volume. That quantity, which we call loudness, has a physical property that is measurable that we call the intensity. And the intensity is a measure of how much compression the air molecules have, and as a result also how much rarefication there is between those compressions that determine the loudness. So we get a sinusoidal or an up and down variation in the pressure due to the density of molecules being very high in some places and low in the others. When those very dense molecules, densely packed molecules, all traveling at the speed of sound, which is 330 meters per second, arrive on the eardrum, then a more dense compression of air molecules hitting the eardrum at that velocity will apply more pressure. So it's really what we sense is the pressure of the air molecules on the eardrum, which is a result of the compression of these molecules moving at the speed of 330 meters per second. Now when we quantify this in terms of measurable amounts of amplitude, or we've talked about compression of the air molecules and how compressed they are determines how loud it is. When we quantify this compression of air molecules in terms of intensity, we end up with a unit that's called in what's given by watts per meter squared. We characterize them with this number, and the lowest that we can detect with our ear is approximately 10 to the minus 12th. This would be 1/millionth of 1/millionth watt per meter squared, which is a quite small number. This is what we would barely be able to detect if we had perfect hearing and we were in very good physical shape. But when this intensity gets louder, at some point it becomes painful for us to listen to that. We have to cover our ears when we reach the threshold of pain, and that threshold of pain is about 12 orders of magnitude higher than the threshold, which is a million times a million times more strong or loud than the weakest signal that we have. So our ears actually detect a very, very large range of signals, a very large range of intensities that are perceptible to the human ear. Now, because the range is so great, the intensities are scaled by factors of 10, with the barely audible one here at the bottom You see at the bottom the intensity is 10 to the minus 12. And as a reference, this is called a 0 bells, named after the famous Alexander Bell that invented the telephone. The sound 10 times more intense would have an intensity of 1 bell. So if I go 10 times more intense or higher volume or higher loudness than the threshold of hearing, I would get to a noise level that's sort of like comparable to listening to the rustle of leaves blowing in the wind. If someone is whispering in our ear, that is 100 times more intense or louder than our threshold of hearing, and we give that a number specified as a 20 or 20 decibels. If, etc., as we go up here, that every time we increase an order of magnitude, we add 10 to the decibel sound level, which is measuring another way of equivalent measuring the intensity. So these two are really interchangeable, and they are physical measurements of how intense the sound is, and it gives a quantitative explanation of what we normally call the loudness. So sound intensity is a purely objective, and it's a physical attribute of a sound wave. It can be measured by various acoustical instruments, whereas loudness, which is what we associate with sound intensity, is our common experience, similar to pitch and timbre, is a subjective sensation. So all these three qualities that musicians may talk about, which are loudness, pitch, and timbre, is what we would call, as a physicist, a subjective sensation that could be quantified by the intensity in decibels, the pitch in frequency, and the timbre in how much contribution is there to frequencies that are higher than the base frequency of the fundamental that we call the pitch. And it's also true that the ear senses some frequencies much better than others. A 3500 hertz sound at 80 decibels sounds about twice as loud to most people as 125 hertz sound at the same intensity. So simply by changing the frequency, we have the perception that the loudness has changed, but in fact the intensity has not changed. It's only our ear perception that has been our ear sensitivity is much better at 35 hertz than it is at 125. And humans are most sensitive to this particular frequency, even though we can detect signals as low as 20 or 30 hertz and up to 10 or 20,000 hertz. This seems to be the number that our ear is most sensitive to. I think we've already covered this difference in quality, and I've already gone over the difference in the higher harmonics that you get between the piano and the clarinet, so I won't go through this one again, but simply point out that the quality of a tone is determined by how much intensity there are in the various partials. This is just a list of the instruments that we normally deal with. We have stringed instruments, which include the whole array of things that you've heard and seen before, from harps to violins to guitars and pianos. But we also have vibrating air columns, which are set up by fifes, flutes, piccolos, church organs, things like that. And then there's woodwinds that produce streams of air produced by musicians that sets a reed vibrating, such as a saxophone, for example. Percussions are another one. They have a two-dimensional membrane. As they vibrate the air molecules around them, and they amplify the sound that way. And we can change the pitch on the drum, as one example of percussion, simply by tightening we can increase the pitch by tightening the material that's pulled across the top layer or the top portion of the drum. So this basically is showing you that we know that we get some very pleasant and interesting sounds when we combine different types of instruments together. And even though they are played with in the same key, they have a much different structure of their higher harmonics, and when added together, they look even different still. So finally, we're going to talk a little bit about the mathematical portion of these higher harmonics. And I'm going to give you a little bit of background on the mathematician named Fourier, who discovered a mathematical regularity to the component parts of periodic wave motion. And he did more than that, actually. He found that almost any function that is periodic and repeatable, or any physical property that repeats itself over time, can be broken down into sine waves of different frequencies. And he found that even the most complex periodic wave motion can be disassembled into simple sine waves that we'll add together. So breaking these complex periodic structure into individual sine waves was a very, very big point in advancing our understanding of music and sound. If I go back a slide, we take, for example, the clarinet. The clarinet or the oboe has more than one frequency present, but because it does repeat itself over and over, or will eventually repeat itself if we continue to look at the time later and later, if it's a repeating structure, we can find out, break it down and say, this is really just a sum of regular periodic sine waves that oscillate up and down like the standing waves on the string, but there are multiple of these frequencies, which we have already discussed as harmonic. Now, when the pure tones are sounded together, they combine to give the tone of a violin. So this is just repeating sort of what we said. We have the fundamental frequency of the instrument, the second and the third, and then we add them together. We get a time display that will show us what is the periodicity of the compression of the air molecules. And this could be as a function of distance at a fixed time, like a snapshot in time. And if we look at it that way, then we can see that the places that have the highest pressure are located periodically along a line from the source being over the left, the listening device over on the right, and these compressed air molecules are traveling from left to right. And this periodic structure is what we call a pure sine wave, but when we add them together, we get a much more complex structure that can be created by adding them together. So lowest frequency sine wave is the fundamental and determines the pitch. The higher frequency waves are the partials, or the higher harmonics, that determine the quality. That is to say, how much of the third harmonic is added into the second, and so on. In this particular case, the fundamental has the highest amplitude. That is the most loudness. The second harmonic has the height of the peaks is smaller, so they actually have less loudness than the fundamental. And the third one has even smaller amplitudes, which means that the loudness that's being, or I use the word loudness, but the intensity being added in is even less than the second. But when added together, they give this unique sound. Bottom line is that any periodic waveform, and this is what we call a waveform, can be decomposed into a sum of simple sine waves, all of which contribute differently to the intensity. And this section now. So at this point, we are at the end of chapter 21. You should be working the problems for this chapter and paying attention to the due dates so that you don't get behind. When we resume again, we will start our final and last section, which will be on electricity and magnetism.